Hello. In this video, we will talk about hypothesis testing of coefficients in a multiple linear regression model. So when we have estimated a multiple linear regression model, usually we want to check if the individual coefficient is significant or not. So this is called hypothesis testing of the coefficients. So we use matrix notation for multiple linear regression model. So these are matrix type. Y is n times 1 size of matrix. Actually, it's a column or say column matrix. And X is a matrix with n observations and k variables. And beta is a row matrix with k variables, and this epsilon is the variance matrix. So this epsilon, we hypothesize that this is normally distributed with variance sigma square. And this matrix is very important to be used in coefficients estimation. So actually it's the inverse of the transpose of independent variables matrix. So this comes from the information for all the independent variables. So after the regression model has been estimated, we get the point value of the coefficient bj for all j from 0 to k. So this is k plus 1 coefficients. Then these coefficients are normally distributed with the mean called beta j, which is in regression model for the real value, and with a variance called cjj times sigma square. So cjj comes from this matrix. So each coefficient theoretically follows a normally distributed distribution with the beta j real value, and this is the variance. But we never know this one, and we never know the variance of the epsilon, sigma square. So what we can do is only use the test statistic called t, which is the point value beta j minus this is the value what we want to test, and divided by the projection of two parts. The first part is the square root of cjj from this matrix, and second part is the s. S is sum of square error. This is called SSE, then divided by n minus k minus 1, then take a square root. So S is actually a point estimate or unbiased estimate of the square root of this variance. So because we never know the real value of sigma square, we use S here. So this statistic follows a t distribution with n minus k minus 1 degrees of freedom. So we can use this statistic to test the hypothesis of the beta value. So say if we want to test if this beta coefficient is equal to a specific value, and this is the null hypothesis. For example, this is 0. So if we want to test the beta j equals 0 or not, so we formulate alternative hypothesis is beta j not equal to this value, not equal to 0. Then if we get the statistic from t from the last page, if this t is located at both ends of critical value in the t distribution density curve, in the shaded area for both sides, but here will be, if we test two sides, this is half alpha. So say if alpha is 0.05, so this area will be 0.025, and other side also. So if the t value is very large or very small, then we will reject null hypothesis and will in favor the H1 alternative hypothesis, which means we conclude beta j is not equal to this specific value. So next we look at an example. The percent survival rate of sperm in a certain type of animal salmon after storage was measured at various combinations of concentration with the material used to increase chance of survival. And the data shown in the table in the next page. And the question is, we want to test beta 2 equals minus 2.5 at 0.05 level of significance against alternative hypothesis that beta 2 larger than this value. This is the data table y, x1, x2, x3. This is a multiple linear regression with 3 independent variables. So from the question we formulate, this is a null hypothesis, beta 2 equals minus 2.5. And alternative hypothesis is beta 2 larger than this value. So this is a one-tail test. It's different from what we have seen in the previous page with two-tail tests. So this is a one-tail test. So which means we only want to test here. So all the 0.05 alpha level stay here. So say if we get the t statistic value in this area or get the p-value less than 0.05, then we will say reject the null hypothesis, right? So we do not need to take care of this side, only this side. So we just fill in all values from the estimation. So this is the point estimate for the beta 2, and we minus this value, actually is plus 2.5, then divided by s. S is the sum of square of error, then divided by n minus k minus 1, then take a square root. And this is the C22 from the independent variables matrix, the multiplication for the transpose and inverse matrix. So this value from this matrix, so we get 2.39. And we calculate probability of this statistic t distribution larger than 2.39 is 0.04. So this is the p-value from the data. So if we can see the p-value is less than 0.05, so which means this t statistic is located in the shaded area in the t critical value on the right side, right? So we conclude that we will reject H0 and in favor of H1. So say we conclude that beta 2 is larger than minus 2.5.